Microfluidics is a way of controlling and manipulating the forces on cells, in creating small droplets, working with small amounts of material that would be difficult with say a traditional liquid handling approach, right? So you're trying to do things at a micro level, but you're also trying to do them with high throughput.
Okay, so we are at Frontier Tower. We are with Morgan, and we're going to talk about microfluids. So, what's the difference between the modern microfluid and the more traditional one?
Well, so in the traditional case, a lot of the work around microfluidics is for both bioassays as well as, say, cell morphology assessment and things like that. Like kind of med tech and pharma applications where you don't necessarily want any of the materials to stick to the walls, right? So what we're doing here by creating collagen microfluidic chips is that now the cells, you can perfuse the scaffold of this microfluidic chip and use it for tissue engineering, tissue growth.
But what 3D bioprinter and how does it work?
Well, 3D bioprinting is an extrusive process where you're building up layers, right? So when you're doing, this is very similar to the kind of manufacturing that's used in semiconductors. In this case, you've got an object that you've perhaps created in a CAD environment, and then you process that through a slicer that produces the instructions for a 3D extrusive printer to build up via layers. Some of that is also, again, if you're doing traditional 3D printing, you might need some scaffold to hold the 3D object because it's going to need to have internal support, right? When we're printing inside of gel with the fresh printing, we're able to ignore ignore gravity, if you will, and print in 3D because we're printing inside a bath.
Do you want to explain us this picture?
So this is one of our examples that we got from the CMU course, where we used a STL file of something that would be quite a traditional microfluidic chip with a 2 inlet serpentine 1 outlet structure. We printed that in a fresh bath. Fresh is an acronym, and then
an acronym of what?
Now, free-form reversible embedding of suspended hydrogels bioprinting, right? So this allows you to print soft biomaterials, and that's the real innovation that CMU pioneered. And in this case, we've printed the chip, we've used a collagen bioink, and we've now heated up the fresh bath, and so that we can now draw off the liquid and leave the chip. So now the second stage is building a bioreactor for the chip itself. Okay, because you've used a soft material to create this, like now connecting it to the piping from your peristaltic pumps is something that requires a little bit more infrastructure than we would with a traditional microfluidic chip.
What's a question on microfluids that you wish people ask more but nobody do?
Again, my particular interest is around tissue culture, tissue engineering. So what's interesting about microfluidics, and when we can do it this way, is that you can now give cells the microenvironment that they would have naturally. So, for instance, having a fluid flow allows endothelial cells to better organize themselves, to produce the kind of channel lining that would be similar to the kind of vasculature that you'd find in normal tissue. We are still quite far away from printing organs.
Definitely.
So, what's interesting and what we can describe, or what we can work with some of the newer bioprinters, is combining multiple inks. So, what you really want to see with an organ like say skin is how to both provide all the different cell types that are involved in an organ like skin, as well as how to control their growth and direct the 4D bioprinting. So in some cases you need additional layers just to actually prevent growth in certain directions, as well as providing scaffold to encourage growth in other directions.
Thank you.